Hi, everyone. In this third lecture for Unit 4, we're going to look at exoplanets, which are planets in orbit around other stars in our galaxy. So in this lecture, I'll have two primary concepts that I'm going to want you to walk away with from our time together. First, I want you to describe the discovery of planets around other stars, how it works, and then describe the habitable zone. What do we look for when we find planets around other stars? And why is that important for our search for life in the galaxy? So thinking back to where we started with our class, we talked about the solar nebula hypothesis and how these solar systems are starting their journey in these nebula, these clouds of dust and gas. And they begin with forming around these dust disks, and they have these rings. And from there, the planets grow and they accrete into a fully fledged solar system. And then we have the protoplanetary disks, where the young planets are in orbit around stars and they're gathering up the dust and gas that is present, growing larger in size. And so we have images of those early solar systems in their formation. Think of them as the planets as little Roombas going around their star, gathering up the dust and gas. So taking this knowledge, we can then start to look for more of those solar systems with planets around them. And so ultimately, we have gotten better and better at this over time. The first extrasolar planet was discovered in 1996. And since then, we have only been adding to our inventory of extrasolar planets. As you can see here, there was a huge boost in 2014 and 2016. This was due to the new space telescope, the Spitzer Space Telescope, being added and brought online, which was specifically designed to find these objects. And it did a really amazing job to locate these exoplanets. So what do they look like? Well, we don't have great images of them because they're actually really, really hard to see. Because we're so far away, it makes them appear relatively close to their star. And oftentimes, the image of them will be drowned out by the image and the light that is coming from their local star. However, we have been able to identify 44 different planets from direct observations of the solar system. And so here are a couple images. Here's one where we've been able to identify 4 different planets around their star. Usually these planets tend to be really big, so it's easier to see them. Here's one over here, and here's multiple images taken of this solar system in 2004, 2006, 2010, and then 2012, and it's tracking an object's location over time to get an idea of how fast it is orbiting around its star. And then here are other direct observations of planets around their star. Again, these tend to be really large planets, nothing like what we would expect for Earth. If you looked at that chart where it showed the really large increase in the number of planets, most of them were associated with the transit method. The transit method does not attempt to find the planet itself, but attempts to find the change in the light coming from the star by the planet passing in front of it. So we don't actually get an image of the actual planet, but instead we read how the solar light coming from that star changes when the planet goes in front of it. So here, if we see, here's the planet, and then it moves in front of the star, and then it moves away. The light that we would be detecting from that star will dip when the planet goes in front of it, and we can get an idea of just how big it is by how much the light has been blocked by that planet. So far, we've actually found almost 3,000 planets through this method. It's a very easy way to find planets if you have a telescope that's designed to look for them. So we are finding planets almost every day through this method. I wanted to highlight this other method. It's very interesting, could be a future project in the next 20 to 30 years.
The universe is teeming with planets. I want us, in the next decade, to build a space telescope that'll be able to image an Earth about another star and figure out whether it can harbor life. My colleagues at the NASA Jet Propulsion Laboratory at Princeton and I are working on technology that will be able to do just that in the coming years. Astronomers now believe that every star in the galaxy has a planet, and they speculate that up to 1/5 of them have an Earth-like planet that might be able to harbor life. But we haven't seen any of them. We've only detected them indirectly. This is NASA's famous picture of the pale blue dot. It was taken by the Voyager spacecraft in 1990 when they turned it around as it was exiting the solar system to take a picture of the Earth from 6 billion kilometers away. I want to take that of an Earth-like planet about another star. Why haven't we done that? Why is that hard? Well, to see, let's imagine we take the Hubble Space Telescope and we turn it around and we move it out to the orbit of Mars. We'll see something like that, a slightly blurry picture of the Earth because we're a fairly small telescope out at the orbit of Mars. Now let's move 10 times further away. Here we are at the orbit of Uranus. It's gotten smaller, it's gotten less detail, less resolve. We can still see the little moon. But let's go 10 times further away again. Here we are at the edge of the solar system, out at the Kuiper Belt. Now it's not resolved at all. It's that pale blue dot of Carl Sagan's. But let's move yet again 10 times further away. Here we are out at the Aurora cloud, outside the solar system, and we're starting to see the sun move into the field of view and get into where the planet is. One more time, 10 times further away. Now we're at Alpha Centauri, our nearest neighbor star, and the planet is gone. All we're seeing is that big beaming image of the star that's 10 billion times brighter than the planet, which should be in that little red circle. That's what we want to see. That's why it's hard. The light from the star is diffracting. It's scattering inside the telescope, creating that very bright image that washes out the planet. So to see the planet, we have to do something about all of that light. We have to get rid of it. I have a lot of colleagues working on really amazing technologies to do that, but I want to tell you about one today that I think is the coolest and probably the most likely to get us an Earth in the next decade. It was first suggested by Lyman Spitzer, the father of the space telescope, in 1962, and he took his inspiration from an eclipse. You've all seen that. That's a solar eclipse. The moon has moved in front of the sun. It blocks out most of the light, so we can see that dim corona around it. It'd be the same thing if I put my thumb up and block that spotlight that's getting right in my eye. I can see you in the back row. Well, what's going on? Well, the moon is casting a shadow down on the Earth. We put a telescope or a camera in that shadow, we look back at the sun, and most of the light's been removed, and we can see that dim, fine structure in the corona. Spitzer's suggestion was we do this in space. We build a big screen, we fly it in space, we put it up in front of the star, we block most of the light, we fly a space telescope in that shadow that's created, and boom, we get to see planets. Well, that would look something like this. So there's that big screen, and there's no planets, because unfortunately it doesn't actually work very well, because the light waves of the light and waves diffracts around that screen the same way it did in the telescope. It's like water bending around a rock in a stream. And all that light just destroys the shadow. It's a terrible shadow. And we can't see planets. But Spitzer actually knew the answer. If we can feather the edges, soften those edges, so we can control diffraction, well, then we can see a planet. And in the last 10 years or so, we've come up with optimal solutions for doing that. It looks something like that. We call that our flower petal star shade. If we make the edges of those petals exactly right, if we control their shape, we can control diffraction, and now we have a great shadow. It's about 10 billion times dimmer than it was before, and we can see the planets beam out just like that. That, of course, has to be bigger than my thumb. That star shade is about the size of half a football field, and it has to fly 50,000 kilometers away from the telescope that has to be held right in its shadow, and then we can see those planets. This sounds formidable, but brilliant engineers, colleagues of mine at JPL, came up with a fabulous design for how to do that, and it looks like this. Starts wrapped around a hub, separates from the telescope. The petals unfurl, they open up, the telescope turns around, then you'll see it flip and fly out that 50,000 kilometers away from the telescope. It's going to move in front of the star, just like that, creates a wonderful shadow. Boom, we get planets orbiting about it. Thank you. That's not science fiction. We've been working on this for the last 5 or 6 years. Last summer, we did a really cool test out in California at Northrop Grumman. So those are 4 petals. This is a subscale star shade. It's about half the size of the one you just saw. You'll see the petals unfurl. Those 4 petals were built by 4 undergraduates doing a summer internship at JPL. Now you're seeing it deploy. Those petals have to rotate into place. The base of those petals has to go to the same place every time to within 1/10 of a millimeter. We ran this test 16 times, and 16 times it went into the exact same place to 1/10 of a millimeter. This has to be done very precisely. But if we can do this, if we can build this technology, if we can get it into space, you might see something like this. That's a picture of one of our nearest neighbor stars taken with the Hubble Space Telescope. If we can take a similar space telescope, slightly larger, put it out there, fly in a culture in front of it, what we might see is something like that. That's a family portrait of our solar system, but not ours. We're hoping it'll be someone else's solar system, as seen through an occulter, through a star shade like that. You can see Jupiter, you can see Saturn, Uranus, Neptune, and right there in the center, next to the residual light, is that pale blue dot. That's Earth. We want to see that, see if there's water, oxygen, ozone, the things that might tell us that it could harbor life. I think this is the coolest possible science. That's why I got into doing this, because I think that will change the world. That will change everything when we see that. Thank you.
I think it's a really cool video that highlights just the possibilities that exist for finding other planets around other stars. He highlighted some statistics that, based upon the number of planets that we've currently found, it is now believed that 1 in every 6 stars has at least one Earth-sized planet. And that almost all stars seem to have at least some planets. And so we're really kind of starting to learn that solar systems are very common in our galaxy. Planets are equally common around all types of stars. And so ultimately this means that our sun is amongst one of many different types of stars that can host planets around it. When we look at this chart, it seems that most stars or most planets around stars seem to be either similar in size to the shape of Earth or much larger than Earth, say a super Earth or a mini Neptune, maybe 2 to 4 times the size of the Earth. And so if we take this information and then we extrapolate it to this image of the Milky Way, we can really start to see all the possibilities that exist for seeing solar systems and possibly finding life in our galaxy. This brings me to the last point for today, is that when we look at these planets, we really want to identify if they are located within their habitable zone. Habitable zone is characterized as that location within the solar system where it is safe, or it is okay for liquid water. If you get too close to the star, then the water will evaporate and it'll only exist as water vapor. If you get too far away, the water freezes. And so ultimately, if life on those other planets is similar to ours, it requires liquid water. And so we want to find planets around stars that are within their habitable zone. So in this chart, we see different sizes of stars, and then we see different pathways for the habitable zone. For larger stars, the habitable zone can be further away. For smaller stars, the habitable zone is much closer. And here is a sort of a scattering of the different planets that we have found. And some of them do in fact exist within the habitable zone. And then here is a final image that shows just how different these solar systems can end up looking. Here is our solar system at the bottom. And then if we take one of the solar systems that we have found, TRAPPIST-1 system, it actually fits entirely inside the orbit of Mercury. All of these planets, B, C, D, E, F, G, and H, are actually all planets in orbit around TRAPPIST-1. And there are a handful of them that appear to be in the habitable zone. We don't know much more about these planets other than that, but it is promising. And hopefully with new technology, we can start to learn more about them to see what kind of conditions exist and see if they're a good place for life. That is all I have for Unit 4. I hope that you have a great rest of your day. Please reach out with any questions on these lectures or the assignments in preparation for our exam. Thanks, everyone. Bye.